Alright, so we're going to learn about the foundation of logical reasoning. This is one of my favorite things to teach because if you can think logically, that really improves your ability to do just about anything in the world. Now, what is logical reasoning? It's the ability to go beyond the information provided. Why do we want to go beyond? Because if information is limited, and then especially in the world today, we have to be able to problem solve. We have to be able to think critically. We have to be able to infer, to conject, to figure stuff out. So to go beyond the information given. And among the most important words in logical reasoning are the simple words if and then. So if-then statements, or as we say, conditional statements, are really the building blocks for how computers are made and designed. Somewhere a coder or a web designer or programmer writes down code to tell a computer exactly what to do. Here's an example. If the user clicks on a friend's name, we're talking about Facebook here. So if this happens, and we call this the premise, which we abbreviate as P. So if this, then do this thing. If the user clicks on a friend's name, then pull up the friend's page. You guys are familiar with that. This we call the conclusion, which we abbreviate as Q. So if P happens, then Q. You'll see that written sometimes like this. If P, then Q. Come up with another example of an if-then statement. You see them all the time in your own life. For me, I'm going to put if, make one up for yourself though, but if it's Sunday, if today is Sunday, then me personally, I'm watching football. I'm watching football. So if this, P, then Q. Okay? And really, any argument, and we all have arguments about anything, about girlfriend, boyfriend, politics, religion, whatever. If we argue in sports, basically any argument has the same structure. It's P, then Q. We can break down any complex argument by this logic. P, then Q. They start with a premise and end with a conclusion. So let's look at an example where we're using some logical reasoning. We're given an if-then statement. If it's Christmas Eve, then it's December. We know that to be true. Okay, and we said we can abbreviate that as if P, then Q. If it's Christmas Eve, then we know it's December. The converse of that statement, converse means when we switch the premise and the conclusion. So we write that as if it's December, then it's Christmas Eve. And we can abbreviate that as if Q, then P. We switched around the premise and the conclusion. If it's December, it might not necessarily be Christmas Eve. It could be any other day in December. So this is not true. And if something is not true, we need to provide an example, a reason for why it's not true, a counterexample. If it's December, it doesn't have to be Christmas Eve because it could be December the 12th. It could be December 9th, December 8th. It could be any day in December other than Christmas Eve. So this is an example that shows that this one is false. What the inverse means is to negate. Negate meaning to make negative. To use the word no or the word don't. So, and we're just going to make the original statement negative. We're going to negate P and negate Q. So if it's not Christmas Eve, I'm just going to abbreviate. If it's not Christmas Eve, then it's not December. Okay? Is that true? If it's not Christmas Eve, would we know for a fact it's not December? No. No. And a counterexample is we could use the same thing or pick another one, it doesn't matter. If it's not Christmas Eve, it could be December 4th, and that's still December. So this statement is not true. Contrapositive, you're going to do both. You're going to switch and you're going to negate. So you're going to switch it around and make them negative. Okay, it's the negative of this one. If it's not December, November, could be January, then it's not Christmas Eve. Okay, if it's not December, it can't be Christmas Eve. And so that is a true statement. If it's true, we don't need a counterexample. Let's look at a second example. Our if-then statement is if two angles are corresponding, then they're congruent. Just a little thing to point out, this if two angles, this is just the noun. This is kind of English stuff. But really the P is here. Then they're congruent is the Q. Okay, so if two angles, that's just the subject. So each one of these, no matter what we're doing, is we're talking about these two angles. So that's going to be the beginning part. That doesn't get switched around. Okay, try this one on your own. Pause the video and then check your answers. Just remember that converse is to switch and inverse is to negate. Okay, I get those confused, but I try to remember that converse shoes, it almost doesn't matter. You can put them on the right foot or the left foot. They look so much alike, you sometimes mix them up. You could switch them around. So when I think of converses, I think switching. Pause the video and try this on your own, then check your answers. Okay, so your statements should look like this. Remember, we start out if P, then Q. We switch Q and P. So if two angles are congruent, then they're corresponding. And then we negate P and negate Q. And then finally, we do both of these things. And your statement should look like this. Now, two angles are congruent. Congruent meaning equal, meaning they have the same measure. They don't necessarily have to be corresponding. This is not true. Okay, and a counterexample, we can just draw a picture. This angle, we'll say is 80 degrees. You may have another angle that's the same measure of it, but they're not corresponding angles. They just happen to be the same. And you maybe could have drawn or written in vertical angles. Vertical angles are congruent, but they're not corresponding. And then if two angles are not corresponding meaning it could be vertical, then they're not congruent. That's not true either. A lot of times these two happen to be true at the same, happen to have the same truth value. And you can almost use the same example. They're not corresponding. Those are not corresponding. They're not congruent. That's not true because those are not corresponding, but they're still congruent. And then the final one, if they're not congruent, if they don't have the same measure, then they can't be corresponding. And that would be that. All right, moving on to talk about Venn diagrams. Why do we use Venn diagrams? Really, we use them to help us. Okay? They help us. When you get it, it seems complicated at first, but when you get it, it helps you to figure stuff out. And it helps us in more complex logical problems. As things start to get more complex, Venn diagrams are an illustration that can help us, and they can help us to make conjectures. A conjecture is like a logical conclusion, is really all that it is. Is when you figure stuff out. You're given a set of information and you're putting it together to make a conclusion. You're figuring stuff out. And you've probably seen Venn diagrams that look something like this. Those are the most common. And you maybe take something like football and basketball, and you might compare them and say this is how they're different, and then they both have a ball, they're both popular, whatever, and you compare. But we're going to do Venn diagrams a little differently. Our Venn diagram is going to look something, and I'll come over here for space, it's going to look like this. For example, if it's a carrot, then it's a vegetable. A carrot is a type of vegetable. It's not two separate things that we're comparing. This is a type of vegetable. Carrot is a subset or type. It belongs to vegetables. It belongs. Carrot is just one type. Maybe you have down here, you have broccoli. And maybe over here you have cauliflower. And then vegetables, maybe you have another Venn diagram, and I know I'm getting a little carried away, but maybe you have a separate bubble that's fruit. And these all belong to the bubble called food. And so it's just a way of comparing some things. So let's use this Venn diagram for an example. This is the part we want to focus on, the fact that carrots are a type of vegetable. So we put them on the inside. And what you can just do to make it easy is P is always going to go on the little one, and Q is always going to go on the outside. Okay? And so we use this to make some conjectures. Now we're given a statement that something, some piece of food, is a carrot. Well, if it's a carrot, then we know it's in here. If it's in here, then it's also in the big one. So if it is a carrot, we know for a fact, it didn't tell us this, but we know for a fact that it's a vegetable. Because we're conjecturing that. If it's a vegetable, then it could be somewhere in this. It could be a carrot, could be somewhere in here, but it doesn't have to be. It could be broccoli, it could be cauliflower, it could be squash. We don't know. So there's not enough information. And we can write that by just saying we're not going to make a conjecture. There's no conjecture that can be made. Not enough info. If something is not a carrot, if it's not a carrot, it means it's not in this little circle right here. It could be here, it could be out here. It could be over here with fruit. We don't know where it is. So again, we don't really have enough information. We'll just say no conjecture. Not enough info. But if something's not a vegetable, if it's not a vegetable, then that means it can't be in this circle, and it's got to be somewhere outside. And so if it's somewhere out here, it can't be a carrot. We know for a fact it cannot be a carrot. Now for something that's simple as carrots and vegetables, you can pretty much do that without the Venn diagram. But as it gets more complicated, this helps you.